Good day! Today we're going to learn about something really cool called tree data structure. Just like how families have special chart to show who's related to whom, computers use something similar called a tree to keep information organized. A tree is a special way to organize information on a computer. It's like a family tree but for data. Every tree has a special starting point called the root. Alright, young explorer, are you ready to dive into the secret language of trees? We're going to learn some really cool words that help us talk about trees in the computer world. First, let's meet the root node. It is like the king or queen of the tree, standing at the very top. The root node doesn't have a parent. It's the big boss.
Next, we have child nodes. These are like the prince and princess of the tree. Each child node is connected to a parent node, just like how kids are connected to their parents.
Then, there are parent nodes. These nodes have one or more children. They are like the wise guardian, looking after their young ones.
Now, let's talk about siblings. Siblings are like brothers and sisters. They share the same parent, just like you and your siblings share the same mom or dad.
Meet the leaf nodes. They're like the leaves at the very end of a branch. They don't have any children. They're the furthest from the root.
Then, we have internal nodes. These nodes have at least one child. They're like the busy hubs, managing their own set of branches. The degree of a node is like counting how many children a node has. If a node has 2 children, we see it has a degree of 2. Now, let's talk about the level of a node. The root node is at level 0. Its children are at level 1, and their children are at level 2, and so on. It's like floors in a building. The height of a node is like measuring how tall a tree is from a specific branch. It's the number of steps from that branch to the furthest leaf. Next, we have ancestors and descendants. An ancestor is like your great-great-grandparent. There we are in the family tree. Descendants are like your great-great-grandchildren. They come after you. A path is like a trail in a forest. It's the way from one node to another. You follow the edges to find your path.
Lastly, we have subtrees. Each child in a tree creates its own little tree. It's like a tree within a tree, like having your own little garden in a big forest. And there you have it, all the amazing words we used to talk about trees in a computer land. Now get ready to explore the properties that make trees so special in the world of data structure. Get ready to uncover some really cool facts. Just like every tree in a forest has its own unique features, each tree in the computer world has special qualities that make them extraordinary.
Now, let's unravel some of the fascinating properties that make trees so special. One of the cool things about trees is that they always have one fewer line or edge than the number of dots or nodes. The height of a node is like measuring how tall a tree is from a specific branch. It's the number of steps from that branch to the furthest leaf. Think of it as a tree's ways of telling us how high it can reach. Now, let's talk about the depth and height of a tree. It's like figuring out how tall a tree is and how deep its roots go. The depth tells us how many steps we take from the top, while height measures how tall the tree stands. Now, let's talk about the degree of a node. It's like counting how many children a node has. Can you guess the degree of the leaf nodes? That's right! The degree of a leaf node is always 0 because they don't have any children.
Alright, fellow adventurers, get ready to explore the incredible diversity of tree structure. Just like there are different types of animals in a forest, there are different types of trees in the computer world. Now let's embark on an exciting journey to discover the different type of tree structure. First up, we have the binary tree. In a binary tree, each node can have a maximum of 2 children linking to it. It's like having 2 branches of each tree. Next, say hello to the ternary tree. This special tree can have at most 3 child nodes, usually distinguished as left, mid, and right. It's like having 3 branches for each tree. Now let's meet the n-ary tree, also known as a generic tree. This tree is a real team player. Each node can have multiple child nodes and it doesn't set a limit. It's like having lots and lots of branches for each tree. Imagine this tree is like different type of forests. Some have only 2 kind of trees. Some have 3 and some have the whole variety of them. Within the world of n-ary tree, we can find general tree. This type has no specific constraints on its hierarchical structure. It's like a wild and wonderful forest where trees grow however they want. So to sum it up, we have binary tree with 2 branches, ternary tree with 3 branches, n-ary tree with a lot of branches, and the general tree with its free-spirited forest. Isn't it amazing how there are so many types of trees in the computer world? Each one has its own special way of branching out.
Now that we've met our tree family, let's learn the magic spells that help us interact with them. These are the basic operations that make trees even more amazing. Imagine you have a magic wand that can do 3 special things: create, insert, and search. These are like the superpowers of tree wizards. First up, we have create. This is like planting the seed of a tree. We start with an empty space and let our tree grow. Just like a gardener plants a seed in the ground, we create a space for our tree to grow and flourish. So, create is all about giving life to our tree. It's like saying abracadabra and watching a tree sprout up. Next, we have insert. This is like adding more branches to our tree. We can make our tree even bigger and more complex. Just like an artist adds more colors to their painting, we can add more branches to our tree to make it even more beautiful. So, insert lets us expand and grow our tree. It's like adding new chapters to a story, making it richer and more interesting. Finally, we have search. This is like having a special treasure map that helps us find exactly what we're looking for in our tree. Just like a pirate uses a treasure map to find hidden gold, we use search to find specific information in our tree. So, search is our compass in the forest of data. It helps us find the hidden gems we're after.
And there you have it. With create, insert, and search, we became true wizards of the tree world, creating, expanding, and uncovering treasures.
Wow! We've had an incredible adventure today, exploring the magical world of trees in computer science. From understanding the basics of tree structures to discovering their real-world applications, we've covered a lot. We learned about the different types of trees, how they grow, and how they help us organize information. I want to say a big thank you to each of you for joining me on this amazing journey of learning. Remember, the world of computer science is full of fascinating concepts waiting to be explored. Keep asking questions and seeking knowledge. Until our next adventure, happy exploring and may your curiosity never stop growing.
Now, let me ask you a question based on our presentation. Why trees are important in data structure? Trees as nonlinear data structures are important for several reasons. First is the hierarchical structure. Trees provide a natural way to represent hierarchical relationships. This is crucial in various applications where data has a parent-child relationship, such as in file systems, organizational structures, and family trees. Second is sorting. Binary search trees can be used for sorting data, which is a fundamental operation in computer science. It allows data to be organized in a way that makes it easy to access in sorted order. Third is graph representations. Trees are a special case of graphs with no cycles. They are used as a foundation for graph algorithms and data structures, and many graph problems can be reduced to 3 problems. Fourth is complex hierarchies. Trees can represent complex hierarchies where nodes can have multiple parents or children. This is useful in representing things like web page structures, organization charts, and project management dependencies. Fifth and last is the memory management. Trees are used in memory management where they represent the hierarchical structure of memory allocation, like in the allocation of memory to processes in an operating system. What are the positive and negative aspects of trees? Trees as nonlinear data structures provide a hierarchical arrangement that excels at representing intricate relationships between items. They enable efficient searching, insertion, and deletion operations, making them valuable in various applications, including file systems and organizational charts. Trees also offer advantages when it comes to sorting elements through in-order traversal. However, their implementation and maintenance can be complex, and they typically have a higher space overhead due to the need for pointers and links. Unbalanced trees can lead to inefficient operations, and their suitability for specific applications might vary, potentially causing memory fragmentation due to dynamic memory allocation. Consequently, careful consideration is essential when selecting a tree structure for a given problem.